So is there anyone, I don't want to waste a lot of time doing things that folks know. Is there anyone here that doesn't know my company or needs an introduction? You can raise your hand. That's encouraging. Okay, so I can say a little bit about Soundsmith. Soundsmith has been around for 47 years, and it's been a mentoring company. I've had a love affair with audio since I was 3 years old. And my best friend when I was 3, other than my white shepherd, was a wind-up that was a bit of a luggable that I carried around everywhere I potentially could, listening to 78s. And I just remember being utterly fascinated with this device that was completely acoustic, completely mechanical. And even at a tender age, I understood Edison's genius and what he'd done in creating an acoustic fulcrum. He had matched the mechanical impedance of the air to a stylus and a dancing groove. A large force over a small area converted to a small force over a large area by a teeter-totter, an acoustic teeter-totter, so clever. Could have been done thousands of years before. Quite fascinating. And it was that experience, it was that emotional understanding that really led me, and a love of science and music that led me into a lifetime of trying to invent things, trying to create things, to perfect things, to understand the flaws in things that people had designed and how to make them better. But Soundsmith has been a mentoring company because, frankly, this is a dying industry, and anyone who doesn't know that doesn't have their finger on the pulse. We've lost so many wonderful engineers. I'm graced today to have one of my mentors, I used to say one of my former mentors, but he reminds me always that he's still my mentor, and of course he is. And that's Richard Majestic, sitting up front here. I joined Ram Audio in the 70s after having a repair shop, and was Richard's production engineer, and I got to contribute to some of the designs, and it was an amazing experience. And so I went from there to working at Bozak. I was director of engineering at Bozak for 3.5 years. I worked with Rudy Bozak. He was amazing. And again, an empirical engineer, an intuitive engineer. And you know, one of my favorite memories was designing a loudspeaker and having him come over and listen for about 30 seconds. And then he put on his felt cap and went to leave the sound room. And he turned and he looked at me and he said, you know, if you're designing an electromagnetic transducer, there are 10 things you'd like to do. You're only going to get to do 3 of them. So you'd better damn well pick the right things. And he turned on his heel and he left. And I thought he had dissed me, but I realized he'd really imparted a lifetime of wisdom on me, because I've tried to carry that forward. And that was one of the lovely things about working with Richard at Ram Audio, because Richard knew the right 3 things to put at the top of the list. He generally did. And if you do that, and you do that with all of your designs, magic happens. I do it with my speakers, I do it with my electronics, I do it with my cartridges. And if you do it right, the products stand on their own, but when you put it together, the whole is greater than the sum of the parts. And that is an amazing experience. You often don't hear that in audio rooms. People think if you take an engine from a Maserati and a frame from a Rolls Royce and a transmission from pick a car, and put it together, you're going to wind up with something wonderful if you throw enough money at it. And that's not true. It's not true. It really requires insight and engineering. So, enough said. I'm going to read this. I worked, after Bozak, I worked at IBM Research for 11 years at the T.J. Watson Research Center. An amazing experience. IBM took the Nobel Prize for a number of years running in low temperature superconductivity, the scanning tunneling microscope, which I got to work with in my group. And then I worked with advanced low energy chip packaging for 8 years. I got to invent a lot of stuff. I had 3 labs. I had a ball. But I kept Soundsmith going as a mentoring company because this is a dying industry. And a lot of the people that I've taught who were my students, Jeff Joseph used to come to my house when he was a kid, and I taught him, gave him electronic lessons. Your mothers were bringing the other kids for piano lessons. Jeff got dropped off at my basement. So I continue to keep Soundsmith as a mentoring company, and it is a drop in the ocean, but it's something. And some of the people I've taught have gone on to stay in audio, and that's a wonderful thing. So I was asked about a week ago by Bill Liebens of PS Audio to write an article about analog for his magazine Copper, and he said, I just can't find anyone to write anything about analog, so I'm going to read this to you. It kind of explains my relationship to analog a little more clearly. A wise man once said, the most difficult thing there is to do in the world is to separate a man from his suffering. Had I heard that earlier in life, I might have chosen another profession. It's a point of utter fascination that if one looks backwards at one's life, it often looks remarkably well orchestrated. It's only when one looks forward that things look a little dicey. Such is the nature of analog design, especially when it comes to miniaturization. When you trace the developments in analog from the beginning of time, it would seem that very few detours were encountered. That, in and of itself, suggests a preconceived pathway, a portal, a once appearing mandated a mission. Mankind's best efforts have often been realized by mimicking nature itself, which appears to exist in the continuous flow of time's passage. As it turns out, I've been the willing victim of such hypnosis, spending most of my life engaged with invention and designs that can only be realized through intuition, a steady hand, and inspected with the aid of high-power optics. The development of critically accurate, miniaturized devices intended to interface the tangible world with intangible technology, along with seemingly wasted amounts of wattage and inefficient motors designed to move air somewhat accurately, at first seems a fool's game. It is, in fact, an emotional, unstoppable pursuit in the effort to capture and reproduce the healing effect of music. It is a worship of a subset of creation itself, a pathway one creates to be reminded that there is a place above the chaos that is attainable. Of the two ways to get there, I chose the analog path and stuck with it, for reasons I find remarkably easy to explain. Analog is the most beautiful woman one could ever imagine. No matter how flawed, at the end of the day, she is still beautiful. She is constant energy. She traces the musical notes with a pointed finger, perfectly formed. She is elusive, extremely difficult, remarkably evocative, and so overwhelmingly devastating when she gets it right. While the ones and zeros attempt to capture an evasive reality and home in on their prey, analog entices, beckons, calls like a siren to its possibilities, and harrowing trespass. Sail through these waters poorly, and you will not pass unscathed. But done with wisdom, luck, and perseverance, one can pass into a new world. If you had heard good vinyl with a reasonably good cartridge, you have met her relatives. If you've heard a full analog disc with a very good cartridge, you've been invited to the wedding. If you've heard a direct-to-disc on a great system, you've met her children. If you've heard a live analog signal cut into lacquer, then removed from the cutting lathe and played with a strain gauge cartridge, she's taken you by the hand and walked with you into the garden, and you will never forget that you cannot understand how all the stars and moons have been melted to make her eyes. No amount of ones and zeros could be more than a clone with some serious DNA aberrations. As evidenced by many, her charm persists even when she wears worn-out jeans and an old sweatshirt. In terms of engagement, as with any woman, it's not what you say, but what you do that determines if she will take your arm and travel with you. It is your commitment, your perseverance, your highly visible determination to be willing to accept failure and continue as if that was part of your plan that entices her. She does not respond to lip service, does not respond to empty promises, will not look your way again if you are unwilling to accept her every beauty mark, her constantly changing mind. Analog is a kite that is directed by the constant wind, and if you wrap the string around your finger and place it near your ear, you will hear the angels directing her movements. If you never considered her, she will never consider you. If you found her simple and old-fashioned, you have perfectly managed to miss her allure. Does she require that you hold her gently and follow the rules so as not to cause her harm? You bet. Does she ask to be poured slowly from the bottle, decanted and slipped like a talisman, and sipped, like a talisman of effort, as opposed to downing a shot of whiskey with a predictable after effect? You bet. Do you wake up from your session with her with your feelings intact and informed? You're darn skippy, you do. And if you're very, very smart, you will never lose her. So that explains my relationship to analog. Now that I've raised it up, I'm going to knock it down. So this talk is called Reproductive Private Parts, and it's a little bit tongue-in-cheek, so I somewhat apologize for that, but not fully. Because I've really not seen cartridge manufacturers been willing to talk about what goes on inside a phono cartridge. So they are reproductive parts, but they're private because they're trade secrets, and people really don't want to talk about the problems. Well, now that I've just praised analog as much as I know how, I'm going to knock it down. I'm going to point out all the difficulties, why she can be extremely difficult, and what Soundsmith does to try and move those things along, not in a small way and not for marketing, but in a real way, in a real tangible way. So I have a question, but Richard, you can't answer this, and Lynn, there's two of the brightest people I know in audio are not allowed to answer this question. Sorry. So does anyone in the room know what causes groove noise? I'll take any response you folks have. What would you think causes groove noise? It's awfully quiet. The signal of noise just got really terrible. I'm sorry, friction, okay. Everybody pretty much agree with that? Okay. That's a logical, clear thought. The answer is actually wrong. It was pointed out to me that groove noise is caused by resonance of the cartridge. It's caused by jitter of the stylus in the groove. This was an amazing thing that was imparted to me because I didn't, again, prior to that, I thought, well, it's friction. You're dragging a rock through a plastic groove. It's got to make noise. No, it doesn't. No, it doesn't. It's fascinating. So the heart of what I want to talk about is exactly that. What goes on at the stylus to groove interface and what goes wrong at the stylus to groove interface and how you can fix it and how you can prove that you've done a good job addressing these things. I'm talking about stylus jitter. So everything that has mass and is suspended has a natural resonant frequency. A cantilever and stylus, your cat, your dog, your spouse, your car, everything has a bell, everything has a natural resonant frequency, a frequency at which it likes to kind of resonate, a standing wave. This is what rips wings off aircraft, for those of you that flew here like I did. It also makes bridges fall down. Standing waves, well, they exist in phono cartridges quite a bit, and they're dependent on the mass of the moving system plus the stiffness of how it's suspended. And as soon as you introduce any energy into the input end, the stylus, it goes into resonance. And that stylus is sitting there banging its way in the groove. So you may say, well, why doesn't it just dump that energy into the record? It can't. That's called a mechanical impedance mismatch, and we're going to talk about that. When you take a large amount of energy and you dump it into a low mass that's restrained, it's not going to move the record. So by the laws of physics, it has to leave the groove wall and bang its way down the groove. And every time it hits, it dumps the energy, because that's what it needs to do. So that's what we're talking about here. Cartridges, we'd like to think of them as being analog systems, but they're not. As painful as that is to realize, they're not, they're digital. They are sampling the groove wall, and since they are velocity generators, they're magnetic generators, like that thing you had on your bike when you were a kid, and the faster you went, the brighter the headlight went, it's a velocity generator. So even though it's sampling the groove wall, it's integrating that signal into a waveform that's supposed to represent what's on the groove. That's as good as it can do. And there are some designs and cartridges that don't work well because they spend very little time sampling the groove wall. This is painful to hear for those of you that love analog. The woman I described is now weeping. So, all right, so let's start, and let's see if I can pull this up. So for those of you that have never seen an SEM, scanning electron microscope, of a stylus in a groove, I want you let go. There it is. Wow, it's amazing. You turned the lights out, my microphone started working again. I don't understand electricity. So this is really the tail wagging the dog in the most amazing sense that you can think of. This is just the tip of the iceberg here. And of course, it's out of proportion because an SEM will do that, so it's a little compressed. But nonetheless, I want you to begin to appreciate the tiny portion of the stylus that's touching the groove walls. And by the way, people that say you don't need anti-skating, they don't believe in UFOs either, probably. If you take your stylus tip and put it on the surface of the record near the runout groove, and your arm's on it, that thing's going to be flying in or flying out. Do that experiment. And then think about translating that force down to the tiny surface area that's here, that's touching this thing. Yeah, you need anti-skating. You've got to get the force on each groove wall the same. Okay, so let's move on. Here's just a lovely photograph. I love this thing. Somebody created this, not me. This begins to give you an idea of the scale that you're talking about. Look at the contact area. This is a bonded elliptical. This is a cheap stylus. Look at the contact area between the scaled groove wall and the stylus swaged through an aluminum cantilever. You're not even looking at the whole cantilever, much less the mass at the other end of it that has to generate a voltage. It's unbelievable. This shouldn't work. It's a miracle that it does, otherwise I'd be out of a job. So, but I want you to get a feeling, the idea of this talk is to get a feeling for the scale of things and the problems that happen because of it, and what we've tried to do. This is a lovely article from Ordofon. It's just a piece of it. You don't have to read the whole thing, but there's some things in here that are just mind-boggling. Look at the middle, the displacement of a 10 kilohertz signal 50 dB below peak level of 10 centimeters displaces only 0.005 micron, 50 times the diameter of a small hydrocarbon molecule. It says the scale is almost impossible to grasp intuitively, but a cartridge can trace it, and the signal, when amplified, can be easily heard. Now here's the telling statement, and it's telling because I heard my good buddy Frank Schroeder give a talk yesterday, and he talked about tone arm design, and there are a huge number of aspects of tone arm design that are exactly applicable to cartridge design, because what goes on between the stylus and the cantilever and the cartridge is very analogous to what goes on between the cartridge and the tone arm wand and the bearings. It's fascinating. Two systems, one miniaturized with a lot of the same challenges and problems. So read the next sentence. It says, certainly any vibrations in the record playing system significantly greater than 005 micron can be expected to distort the cleanliness of low-level, high-frequency reproduction. Of course, we all know there's nothing up there that's of any value anyway, just imaging depth and, fill in the blank. So a designer absolutely must control all spurious vibrations, be they generated by the commonly considered external sources, feedback, footfalls, internal mechanical sources, bearing, or the crucial groove stylus energy interface itself. It's what we're talking about. Or you can add the tone arm, which may not work well. So this is a graphic representation of a moving coil in resonance. And it also shows, not even in scale, but just sort of in scale, the amplitude of these resonances. So the top waveforms indicate the ringing that you get with a standard moving coil cartridge. It's typically between 30 and 50 kilohertz. You may say, well, that's not a problem, that's above human hearing. Huge problem, gigantic problem. Why? Because as I mentioned, that energy is going to go back down the cantilever and it's going to cause stylus jitter. More than that, you're going to get some indifference frequencies. So let's say You've got a resonance at 30 kilohertz and at 40 kilohertz. Well, that's going to create a 70 kilohertz resonance. It's also going to create a 10 kilohertz resonance. Guess what? That's right in the top of the audio band. Groove noise. Groove noise and lack of detail because it's spending a lot of time not on the groove wall. It's like a tire on a bumpy road on a badly designed sports car. That tire is going to spend a lot of time up in the air. It's just the way it is. Below it, I'm showing the Soundsmith design, which is a fixed coil moving iron design. Why is the amplitude lower and why is the frequency higher? It's a matter of mass. And I'm not going to name any manufacturers' names because I don't ever do that, but I can talk about systems. Moving coil designs, which dominate the industry, have a ceiling. They have a limit. You can only make the coils so small, period. Below that, you can't go. There have been some attempts. One notable attempt, I won't mention it. It's a good cartridge, amazingly, but it's incredibly fragile, and they break when you look at them cross-eyed. So moving coils have some inherent limitations. What do? Well, we make fixed coil or moving iron cartridges. Where does the design come from? Not me, I'm not that smart. It comes from Bang & Olufsen. Good Lord, Bang & Olufsen, I remember them. Well, they had some wonderful engineers. They had some really smart engineers. And they did a white paper back in the 60s that showed that their moving iron design, a variable reluctance design, could way outperform an evolution of moving coil cartridges. They got patents on it, they had money, they got patents, they sewed that thing up so tight, nobody else could do their design. It was a gorgeous design. What happened? Well, in teaching audio, as I've done for 47 years, one of the ways I've taught audio is service. So we've had a service shop, and we've serviced audio for all that time, and we were authorized Bang & Olufsen servicers. And we saw that they were running out of model after model of cartridge. So through connections we had through B&O in the States, we got to B&O Europe, and it was a little bit of a difficult negotiation because they were between a rock and a hard place. Certain people who've been with Bang & Olufsen for a long time knew they had to keep producing cartridges for their customers. They're going to be terribly disappointed because you can't put a non-B&O cartridge in a B&O turntable. It's a form factor that only fits B&O tables. Whereas the newbies with the company was, tell them to get a CD player. What's wrong with these people? Well, you can imagine the challenge. I asked B&O, I said, can we take over your tooling and make the design? We don't have the tooling anymore. Okay, do you have people that knew how to build these? They're retired. I said, will their wheelchairs reach the phone? A comment that was not much appreciated. So I made them an offer that they thankfully could not refuse. I said, I will do all the tooling, all the research, all the reverse engineering. I predicted when they were going to run out of their last couple of models, because it was old stock. They thought they were going to be buried with them. And I said, in 2 years, I'll have prototypes on your desk, and if you like them, we'll work out an arrangement. And it worked, and we did. And I worked till midnight for 2 years, for 7 days a week, and made it happen. I also realized, looking at the design, I could continue to improve the design because B&O had evolved it over a 30-plus year period, from one series to the next to the next. They kept reducing the mass. They kept improving the magnetic path. They kept improving the performance. And I saw, unlike a moving coil, there was no limit, or not a huge limit, no stopping point in the path to further improving the performance and reducing the mass. I said, this is the design. And since they had the rights, nobody was going to follow me. And frankly, since the whole world is moving coil, how much success am I going to have? So, but that's why this graph is important. Okay, again, here another representation of the moving coil, the amplitude and the resonances. The Atello is our highest mass moving iron, and the Hyperion is our lowest moving mass moving iron. And the resonance of that one is up at 90 kilohertz. So there are two things going on with respect to the Stylus groove interface. One of them, as I'm showing here, is the natural resonant frequency. The other is also a huge problem, and that's reflected energy. So what happens in a system like this, you have an input end, the stylus, and at the other end you have the resonant mass. Oh, by the way, this is a photograph of the smallest moving coil assembly. I repair cartridges for folks in here that are not aware. I've been repairing cartridges forever. So I sit at a microscope, appearingly frozen like a statue for hours on end, and do microsurgery and repair cartridges. Most of what I repair are moving coil. There's a lot of failure mechanisms in a moving coil cartridge. I'll talk about some of them. You'll begin to understand why I don't manufacture them. I don't like them, I just fix them for people. So on the left side, you see the smallest moving coil assembly that's on the market. And on the right, you see my largest moving iron assembly. It's 5 times lower mass. That's huge. 5 times lower mass is 500% less inertia. That's not small. That's huge. And I make one that's 8 times lower mass than this, so 800%. Plus you get a thing where, since you're pivoting from the center, you get rotational inertia. And that's twice that, because the geometry is about twice that. So you're 1,000% and 1,800% lower rotational inertia. It's not, these are not small numbers. So here you have a diagram of stylus, cantilever, moving coil mass, and the graphically reduced moving iron mass, 5 to 8 times lower. And what you see is energy goes very nicely up one direction, thank God, or records wouldn't work. And you have a lot of reflected energy. Why do you have reflected energy? And stored energy. Frank Schroeder, in his talk yesterday, had a wonderful description of the toy that executives used to have on their desk. And it was the series of steel balls hanging from the strings all of us around. And you picked up one ball and you let go and it went whack, and the middle ones didn't move and the other ones moved. One on the end moved out. This microphone keeps coming in and out. All right, so, and he asked the audience, he said, why does that happen? Why do the middle ones hold still? And the answer was that the materials are matched. It's steel against steel, so there's a perfect transfer of energy, and then the one on the end flies out. Makes common sense, makes sense. But here you have a problem. Here you have a coil assembly, and I'm not showing it, but behind it, you'll see it in the next drawing, you have, well, maybe we can go to it. There we go. So behind it, let me go to this one. Behind it, you have a damper, shown here in the upper left. Is this a perfect match of materials? No, it's not. So some of the energy gets stored in inertia, some of it goes into the damper, but an amazing amount gets reflected back down. And that's a problem, because as I mentioned, when the energy goes back down, that's the wrong direction. And the stylus groove interface, that's a mechanical impedance mismatch when you're trying to dump energy into it. That's what makes the stylus spend an inordinate amount of time not in contact with the groove wall. And this is just a drawing of a front view of a moving coil so that all of you understand one signal. These are the vectors. The green indicate the vectors of movement for each signal channel. Now here's a real problem. Well, let me go to this one first. So up on the top you see a moving coil. Notice what happens when you go down on the record. The coil, half the coil comes off the damper. This means that with record warps, or depending on how much you set the vertical tracking force, the effect of the damping changes. This is one of the reasons why people get different sonic characteristics from moving coil cartridges when they vary the tracking force. And they go, oh, I've dialed it up to this, it sounds better, or gee, part of it sounds better at lower trigger. It's all over the place. The damping's all over the place. Below it, you see the Soundsmith fixed coil moving iron design, and the small amount of moving mass is actually bonded to the damper, which acts both like a suspension and a damping material. So when it goes down on the record, the top part of it goes into compression, the bottom part goes into elongation. It's not a perfect cancellation, but you retain constant contact. And the beautiful thing is, when you've reduced the mass so much, you need much less damping to control its movement. That's the key. Lowering the mass is the key to improving performance. both from the standpoint of damping and from the standpoint of reflected energy, and from the standpoint of raising the resonant frequency and lowering the amplitude of the resonant frequency. So, yes?
So that's the difference between the B&O and the modern derivative you have, and old school moving iron cartridges. The moving mass is far, far lower now than it was, say, in the 50s with Pickering or something.
Correct. There have been moving iron cartridges in the back, and some of them, Ortofon, by the way, made a couple of very fine moving iron cartridges, and they're wonderful sounding cartridges. There are a number of companies that stuck their toe in the water and made some moving iron cartridges, and a lot of them were quite good. I want to go back to this one. This is kind of interesting. So what this picture shows is the suspension wire. This is a wire that pulls the coil back into the damper. The damper is kind of a donut, a hole. And the wire is what kind of holds this whole mess in place. So if someone were to ask, well, how consistent is that in production? How well do moving coil manufacturers yank on that wire and fix it in position to give a certain amount of damping for a given model as they come down the production line? Is it consistent? Absolutely not. I repair thousands of moving coil cartridges. I have seen some, and not cheap ones, that were 2 months out of the 1-year warranty, a cartridge that cost or sold for $8,000. And it had not only not been built right, but it changed in 13 months. And I had to retension it. This is not unusual. The other problem, one of the many reasons I don't like moving coil, is that if you have an accident or your skating is set wrong or further things, it will actually bend that suspension wire. It will take a set or get bent. Then your cantilever is going to be leaning off to one side and you're going to have an asymmetry. So lack of consistency in production, easily damaged, that and more are reasons why moving coil cartridges have problems. Everything does, but those are some serious problems. The thing I love about this drawing is that it shows that because the energy is not transferred perfectly, and Frank pointed out a nice analogy, when you look at a fish in the water, you're seeing where you think the fish is, but because of the light interaction with the water, the fish is not where it appears, it's actually in a different position. That's a change in vector. This is what happens with different materials when they're together. The energies travel in different directions. So when you try and dump energy into this coil and get it to move and generate a voltage and a magnetic field, and some of it goes into the damper, a lot of it reflects back down, but it doesn't reflect directly back down. It becomes rotational energy. And you see this in a loudspeaker as well. When I worked at Bozak, Rudy smiled one day and grabbed a strobe light, and we were driving the cone at like, I don't know, 60 hertz or something, and he came over and he took the strobe light and he adjusted it for around 60, so you could see the cone just moving slowly like this, even though it was going at 60 hertz. But the cone wasn't doing this. The cone was doing this. It was pitching and yawing you would never see that if you didn't strobe it. So the energies become rotational energy. You can't control them. So what happens when you get rotational energy coming back down the cantilever? It's very interesting. Look on the lower left, you'll see a groove, and on the left side it shows modulation on the left channel. On the right channel, no signal, no displacement of that groove wall. So that gives you channel separation if your cartridge is working, your stereo cartridge. So you measure channel separation, but hang on, what happens when you get this rotational energy coming back down the cantilever? What happens is, and look at the lower right, you get modulation on one side, but you get the stylus jittering against the groove wall on the other side. And that's easily measured as crosstalk of the cartridge. And a lot of that is caused by this rotational energy. Yep.
And imagine what you get with the jitter is actually a type of nasty modulation noise.
You get a lot of intermodulation, you get a lot of spurious generation of harmonics, you're getting distortion. And I will point out that a lot of people like the way things sound because they're used to them. I'm going to tell a little story here. When I worked with Richard, he made a gorgeous amplifier. It was called the RMAF17. We put it out in the field, and the dealers, a lot of them came back and said, it's bass shy. And we're like, what? huge power supply section, goes down to 6 hertz. What do you mean it's bass shy? And we're sitting around Dick's office, and Dick goes like this. He goes, oh my God. He goes, I know what's happening. He said, our amplifier is a high damping factor, very low output impedance, low feedback design. Everything else on the market, Macintosh, Bose, Crown, they were high feedback designs to lower the distortion. The output damping factor wasn't that high. So every time you drive a loudspeaker, you get what's called back EMF, back electromotive force. It's what dims your lights when the refrigerator kicks on. The back voltage was coming into the amp and getting in the feedback path as positive feedback, boosting the gain of the amplifier at low frequencies. Well, my God, we've got a problem. We've got a RAM amplifier that's accurate and everything else out there is not. How do you sell that? So, moving coil cartridges, yes, to answer your question, if you do a spectrum analysis of them, you will see huge amounts of upper order distortion products that are not on the record. Do people like that? Yep, they call it, oh, it's clarity, it's bright, it's distortion. Get rid of it, it's not going to sound the same. So here's the interesting thing. Audio is fascinating in so many respects. One of them is that you can't name a specification that you can do, a measurement you can do that correlates to the quality of the product. It's a little bit hard. You can do damping, you can do THD, IM, TIM, you can do a bunch of those things, and if they're low, that's generally good, but it won't describe how well the thing is really performing. There is a spec with cartridges that has a chance of telling you how well the cartridge is performing, and that's crosstalk. So a good cartridge is going to measure, pick a number, 25 at the low end, up to like 28. There was a very famous $5,000 cartridge, no names mentioned, that had a spec of 28. I mounted one for somebody and tweaked it, and I only got 28, and I went for $5,000, and I went and looked, the spec was 28 dB channel separation. I went, okay. Better cartridges, 28 to 32. Pretty good cartridge above 32, 32 to 35. Our cartridges typically measure from 35 to 45. What does that mean? What it means is that rotational energy is dramatically reduced. The reflected energy is dramatically reduced. The stylus to groove contact is increased dramatically. The sampling rate is way up. The jitter, the stylus control, that's a direct measurement. Is there a way to make a moving coil get up into the mid-30s? Yep. Yank that suspension wire back into the damper, and I guarantee you with any moving coil, you'll get up into the 30s. What does it sound like? You don't want to listen to it. Dead. It's a successful operation wherein the patient died. So really important spec. Now, people have also said, can I use the devices that are out there to adjust the azimuth of a Soundsmith cartridge, like the phosgometer or Ficret system? I'm friends with both those gentlemen. They're both brilliant people. The answer is unfortunately no, because although some of the cartridges I make that make it up into the 40s and mid-40s, I have one cartridge here, a Hyperion here, that measures 45 dB symmetrically, channel to channel. It's a really good cartridge. But some of them come out where one channel is 44 and the other is 38. Is that a defective cartridge? No, it just gives you a clue at how incredibly difficult it is to get up into those stratospheric numbers and have symmetry. What happens if you use one of those electrical adjustment methods to get the channel separation equal? It's going to be tilted off about 5 or 6 degrees. It's going to be distorting like crazy. So you can't use those things to adjust the Soundsmith cartridge. They're pretty good with other cartridges. Okay, so what have we done to try and improve the sample rate? What have we done to try to reduce the jitter, reduce the noise? I've mentioned one of them, we've lowered the mass dramatically. Makes damping a lot easier. But I always love to find the dark corners. The real life of an engineer is that you never get to perfect things. You just don't. Life is not that wonderful. There's usually somebody hovering over you saying, get it done. There's a pile of bills on the desk if you own your own company like I do that says, put it to market. So if you get it to work, you're kind of happy. That's just reality. But nonetheless, I love to look and say, where is there a dark corner? Where can I make a dramatic improvement? So about 6 years ago, I get a call from Herr Schroeder. He gets me on the phone. And he says, yeah, Herr Ledermann. He always increases his German accent when he calls me, just to amuse me. Herr Ledermann, what is on your research list for cantilever materials? I said, hold up, let me pull it up on the computer. I get down to the third thing, and I said, cactus spine. He says, stop. Where are you with this project? I said, back burner, like about 150 other projects. He goes, you must move this up to the front burner. I said, why? He goes, because I've just put some cactus spines in the mail to you. Who knew? Among the many things that Frank is a genius at, one of them is growing cactus. These things come in the mail. I take them apart under the microscope. I start kicking myself, which, by the way, somebody who's as circumferentially challenged as I am, kicking yourself is no easy feat. The structure internally was fascinating. It was stacked columnar cells filled with desiccated resin. They had a bundle of fibers around them, and the whole spine was a group of these things perfectly tapered down to the tip. Oh my God. So here was this God-made material, this nature-made material that was just absolutely perfect. You couldn't make anything like this. I attached a diamond to it with great difficulty. I made a cartridge, and I did an impulse test on it. Now, when you do an impulse test on a normal moving coil, you get a single pulse, and you get 2 big rings and a couple of other rings. You do it with my moving iron cartridges, you get the pulse, you get 2 small rings on my best cartridge. The Hyperion, the one I did, it went up and down and perfectly flat. I did some other measurements. This material turned out to be a mechanical low-pass filter at 35 kilohertz. What does that mean? Well, let's go back. Here's the Hyperion resonating up at 90 kilohertz. That's its natural resonant frequency with the amount of mass that I've been able to minimize. That energy will never make it down the cantilever to the stylus. It gets turned into heat on the way down like the shock absorber in your car. So now what you have is incredible stillness with respect to the stylus and the groove wall. That's the Hyperion. And I have a picture of it. That's the cartridge, the Hyperion cartridge. And that's one of the first cantilevers that I made with the stylus. And it is, that's a advanced stylus shape. That's our OCL, optimized contour stylus. It's just a lovely animal. It's just a lovely beast. What else have I done to get rid of the mass? Well, when I worked for Richard said one day, he said, I want you to hear something, early in the days of RAM audio. And he put on a Matsushita strain gauge cartridge. And I sat there and my brain fell out. By the way, I've never found it since. This thing did so many things right, but again, it sounded different. And different is not always marketable. Soundwind had trouble marketing the Myconic cartridge because it was a very different animal. You were now going to hear everything that was on the record, good and bad, cut both ways. Wasn't going to integrate out any garbage that was on the record. So Richard made a preamp for the Matsushita cartridge, and we sold those. And the strain gauge had been gone for 30 plus years. So I decided I need to bring a strain gauge cartridge back on the market. There were a couple of motivating reasons. Number one, I didn't have a lot of funds for marketing. And number two, like a lot of the things I've done in audio, it was just the right thing to do. So for those of you that are not familiar, that's the Soundsmith strain gauge cartridge. It has user replaceable stylus, styline. The resonant frequency is up at 130 kilohertz and almost not detectable. And Rene Yeager, who's one of my best friends, Rene, if any of you don't know who he is, he was chief engineer of Lexicon, of DBX, HDCD. When Rene came to my shop and he listened to it, it got 10 notes in, and he turned to me and he said, no stored energy. So that is the strain gauge cartridge. There are something interesting, empirical proof. I just got a strain gauge back from a good customer in Hawaii, and I know how much he listens to vinyl. It was 6 years old. I put it under the scope to look for wear. There was like 10 or 15% stylus wear. 6,000 hours. So that's really interesting. What causes stylus wear? Jitter. I have made strain gauges for Tam Henderson. Let's see if I can find this. Oh, by the way, this is what happens when you talk to your records. That's what it looks like after you clean it. Let's see if I can find this. Tam Henderson found that here it is. He found that, I mean, you can read this, but he's basically wrote me about the strain gauge. He listens to lacquers, he has to. I have a Norman lathe, I have 2 lathes, I cut lacquers. You can play a lacquer with a standard magnetic cartridge about 3 to 6 times before it's completely chewed up, it's unlistenable. I have lacquers I've played 150 times with the strain gauge with no groove noise and no stripping of high frequency, tracking at 2.3 grams. That's empirical further proof that jitter is what causes groove wear, groove damage, stylus wear. The fact that you can play a lacquer 150 times with a strain gauge tells you what's going on between the stylus and groove interface. It's dramatic. So I'm coming to the end. I think that gentleman back there was giving me the cut sign. So to review, we have tried to really further the art in understanding what are the limitations of cartridge performance, what do you have to do to increase the sample rate, reduce the groove noise, and really hear detail that's present that other cartridges simply won't produce. That's what we do, and it's been a love of my life, and I continue to do it, and I'm thankful to people like Richard Majestic, who've been a mentor to me, and other people at IBM Research I knew, and a lot of other people in audio. I've had a ball, and it ain't over yet. So, thank you all for coming. Are there any questions that anyone has? Yes.
What's the layman's description of the difference between the strain gauge and the moving iron?
The strain gauge has no mass at the end of the cantilever. No effective mass at the end, it's all gone. So if you think about a cantilever that's not perfectly, there's no such thing as perfection, but a cantilever that's properly terminated at the tail end, it means the energy that goes up doesn't come back down. That's exactly what you want. You want it to go in one direction. You don't want it to come back. You get rid of this mass and you terminate the energy properly so it dissipates, you get almost no stylus jitter, as evidenced by the fact you can play a lacquer 150 times without damage.
You're using the Cactus?
No, here's a fascinating thing. Frank Shorter and one other gentleman talked me into making a Cactus cantilever for the strain gauge. Didn't improve it. There's further proof. When you get to a point where it's really, really good, not even the Cactus spine is going to help the strain gauge. Interesting, isn't it? It's a darn good question. So I thought about doing it, but it doesn't help. It doesn't need it.
So what is it, cantilever? What is it?
I make 5 different styli for the strain gauge. I make aluminum alloy cantilevers, different styli configurations and shapes. I make ruby, sapphire. Part of the talk I wanted to give, I didn't get to, is stylus tip shape and how that affects the damping at the front end, because that's a fascinating subject. But no time, next year. Any other questions? Yes?
What shape is the stylus on your ruby, your optimized contour stylus?
The optimized contour is a stylus that traces about 85% of the groove wall. I didn't get to some of the pictures here, but Azimuth gets much more critical as you go up in stylus shape, and you get way off. You can ride the horn of the record on the top of the groove, not good, gets real noisy. What does that symbol mean back there?
10 minutes.
Oh, I've got another 10 minutes. All right. So yes, the optimized contour traces about 85% of the groove hole. It's like a cutting stylus. I'm an absolute stylus bigot. I hate conicals. And let me just show this. Okay, well you folks are familiar with a bunch of stylus shapes, conical, elliptical, linear contact, microline. Microline's fascinating. I'm not going to talk about it. But here's a very simple graphical illustration of a conical versus a contact line. The red areas indicate the increased contact area. Here's what's interesting. You can have twice the contact area with a fine line. So if you have twice the contact area, you have half the force per unit area. Now wait a minute, doesn't that mean you'd have to double the tracking force to get the same force per unit area? Yeah, it does. So when you have half the force per unit area with a fine line, how much tip damping do you get versus a conical? These are really interesting questions to talk about. But because if you fit it to the groove correctly, you can actually get a better mechanical impedance or energy transfer, so it damps the tip with half the force per unit area. It's a little interesting to think about. Don't lose as much sleep over it as I did. This gives you an idea, if you look at the bottom contact surface, that a fine line has twice the contact area of a conical. Here's the problem with conicals. So here's a spherical at 20 kilohertz with a groove at the beginning of the record. And there it is. Imagine this round guy that I've just produced. Imagine him at the end of the record. It's not going to fit into the grooves. It's called a radius of curvature problem. I hate conicals. They're just good to align. Here's another problem with a conical. Here's the cutting stylus on top. Notice the contact points. Notice the conical playing the same groove. Notice the contact points have shifted. That gives you phase difference between the channels. Bad. Bad. There's a graphical illustration of that. I hate conicals. Did I say that already? Okay. And again, here's azimuth problems related to fine line shapes. You really do need to set the azimuth correctly. I will point out that the instruments that are on the market for setting azimuth do the electrical adjustment. They're assuming that the stylus is lined up with the generator inside the cartridge. It doesn't have to be. So when you do an electrical adjustment for the generator, that doesn't mean that mechanically you've got the stylus sitting in the groove. What do you want? Mechanically, you want the stylus sitting in the groove. A lot of people take USB microscopes and look at the rake angle. I have a YouTube video that talks about that. They should really be looking at the front of the cartridge and getting the azimuth correct. And wherever the generator is, to lose a little crosstalk, it's going to be what it is. If you really want best fit, you don't want electrical best performance, because it may not be. Yes, Lynn?
I was just thinking that I've seen some very expensive cartridges where the azimuth from the factory is quite visibly rotated.
Yeah,
These
no,
very expensive cartridges.
Yeah, no comment. I get to service a lot of those. And again, this is, don't ever talk to your records. They're not listening. You have to listen to them. I have 2 Neumann lathes, and the amazing thing was holding a lacquer, about to do a direct-to-disc recording, and then I turned and looked at the lacquer and it had spots all over it. I spit when I talk. Maybe I'm not alone in this, but you don't know it unless you have a black mirror in front of you. Your records are grooved, you don't see that you're spitting on them. I never talk to my records after having handled the lacquer, because this is what happens. This is a customer who played one record and he said, this piece of junk you made, and he sent it back, and I took this photo and sent it to him, and I said, don't talk to your records. Because it only took a few revolutions to pick that up. Then I sent him this picture after I repaired his cartridge. Yes?
Talk about rake angle.
Rake angle. Very quick, and I'll do a 2-minute thing on rake angle. Does everyone know form problem? Does anyone here not know why there's a rake angle when required for a record? Hands, no, okay. When you cut a record, you cut it, the cutting stylus is set to 2 degrees, so it's like a plow. So you gouge out a continuous thread of material that a venturi on the cutting head picks up, and the thread goes down into a pool of water and it collects down there. If you were to cut straight, unlike a plow in the earth, you'd cut chunks of material out of the lacquer. You wouldn't be able to gather them. They'd lay on the record, and then as you came around to cut another groove, it would interfere with the cut. So since you have to cut at a 2-degree angle, you have to play back at that angle. That's why there's a 2-degree stylus rake angle, because it matches the stylus cutting angle. Does that answer your question?
Well, that's going to vary with tracking force.
The cartridge, correct. The rake angle of the stylus will vary with tracking force and arm height. And a lot of people use USB microscopes to set their rake angle. but they're setting it in a static condition. They're setting it where it's down on a CD or a record. Well, what happens when you start up the record? Well, the cantilever is going to swing up. So it's not perfect to use a USB microscope to set stylus rake angle because it's going to be different when the record starts playing. There are a lot of things that are going to shift, and I cover it in my YouTube. Yes?
What difference does the electrical resonance of the circuit that you're involved with here have on the jitter?
None. There are a lot of people that believe that there is an electromagnetic effect on the stylus by the cartridge itself. It's so small, it's tertiary at best. There's not good coupling. There's not efficient electromagnetic coupling between the systems. A lot of people think there is. It's a good thought, just doesn't affect things.
What's the best way to normally clean a stylus?
It's a good question. I go to a hardware store and I get a little pack of blue tack, that stuff that you put your kids' posters up on, and I put I squeeze them out in a quarter, about half the thickness of a quarter, and then I place it on the platter and I drop the stylus down 3, 4, 5 times into it. Do that every play. Buy a pack of that, that's several lifetimes supply. You can share it with your friends. And if it gets gunked up, then use some alcohol. But the blue tack works beautifully.
Fantastic.
That's how I do it. And it works great. Yes?
Onslow has a
Yeah, they do. It's a
Japanese.
yeah, it's a partially cross-linked silicone, and I get a lot of cartridges where that has yanked the stylus out of the adhesive. The blue tack has a tiny bit of oil in it, which people have complained about, but frankly, the oil doesn't wet the tracing angle very well, and it creates a nice slippery surface. When you go to clean the stylus, the dirt comes off again. So, yeah, Osno is, again, a very, very strong adhesive, partially cross-linked silicone, and it works until it rips your stylus off the camera. All right. Not to say anything negative about somebody's product. It's a good product, but have I gotten cartridges in where the stylus is no longer there and that people have used that material? Yes. That's why I prefer the blue tack. I don't like Elvis to leave the building prematurely. All right. Thank you all so much. I appreciate your coming.